Hi, my name is Tariq, and welcome to my presentation for the follow-up project in DSC423. Gemstones Company Limited is a successful gemstone trading company. They are looking to increase margins in their business. They currently use experienced traders to use subjective valuations. This doesn't work when the company is trying to scale, so they engage with us to develop a standardized model which can be used to predict prices in gemstones. Further, they want to understand the characteristics of the strongest association to price with the purpose of enhancing decision-making. The objective is to develop a predictive model, and the desired outcome is for the users to utilize the model to predict prices with the purpose of increasing profit margins. An important disclaimer I'd like to make now is that polynomial regression should have been used for this project, but it's not possible for lack of time and lack of knowledge. Consequently, I have attempted to illustrate my ability to fix different types of issues that arise in linear regression instead. For exploratory data analysis, we can see where price is the y variable, the scatter plots on this line here illustrates exponential patterns for most of the predictors. This can't really be seen now due to the outlier, but we'll be able to see it in the residual plots when analyzing the model. Vertical patterns here are also translated to the Pearson correlation table here with negative, very, very low correlation between depth and price, as well as positive, very, very low correlation between table and price. The other predictors have very strong positive relationships with price, all above 0.85, but the problem that arose here is that multicollinearity is present between these dimensions, caret and length, height, and width, and between length, height, and width, which can be seen here. These were flagged and adjusted appropriately when developing the model. So model assumptions based on the scatter plots, we could see that the variables are violating the linearity assumption for 5 of the 6 variables. And in this table here, you can see a summarized table of it. We can start with the normality assumption as is violated due to the curvature of the line here. We also have predicted values, which is violated due to the cubic pattern. And the predictors who didn't have cubic patterns violated the assumptions in other ways. So here, for example, we have table, which showed a diamond pattern, which also violated the assumptions. So therefore, all of the predictors violated linearity, homoscedasticity, independence, and the model, the normality assumption. So ideally, polynomial regression should have been used, but instead we superimposed transformations where y was transformed first. It did not suffice, and thereafter the predictors were also transformed. And after fixing the diagnostics of outliers, multicollinearity, and influential points, as well as the assumptions by transforming the variables, this was the full model. Here we can see that none of the predictors have a width value above 10, but we also removed a lot of the predictors. We only have ln caret as the remaining numerical predictor. We have a normal probability plot here, which fulfills the normality assumption. And I'd like to mention here that there's still a slight pattern here, but we will disregard this. And this is because we logged price and carets as well here, which only shrank the values. So the pattern still exists, but it's only shrunken. So we superimposed the transformation and moved on with the purpose of developing the model. After fixing the diagnostics and assumptions, we saw significant increases in R squared, adjusted R squared, the F value, the model is statistically significant, and the RMSE there, 0.13, which I accidentally blocked, is low enough to be deemed good for the model. But remember, we shrank the value, so RMSE will also shrink because it's the error term, but it still shrank enough for us to be happy with that full model. So for the final model selection methods was backwards and CP methods. We had a data split for 60% for training, 40% for testing. Same model was provided by both methods, and this is the final model. To answer the first question of the company, which are the top 3 strongest predictors for the response variable, we have ln caret and DSC3 dummy variable, DSC4 dummy variable. The DC variables in general were some of the strongest predictors, where DZ, for example, are weaker, which we can see here have the lower values, DK as well, some of them. Nevertheless, the top 3 strongest predictors are ln caret, DC3, DC4. Final model interpretation. This is the final model here again. And we can start with ln caret, which is the only numerical variable. A 1 unit increase in ln caret is associated with a 1.89% increase in ln price. Here it's important to remember that both of these are in ln format, so this directly translates to an effect on ln price. For the dummy variables, I'm only going to go through the first one and the base, and the same logic applies for the remaining ones. So for DZ, the cut of the cubic zirconia, the base is fair cut and DZ1 is premium cut. So if a zirconia has a premium cut, ln price increases by 0.88, where fair is the base. And DZ4, for example, here, if a cubic zirconia is ideal, ln price increases by 0.17, where fair is the cut. Fair is the base. These are all in from best to worst, all of these. And for dummy variable dk, which is color, base is J color. dk1 is if a cubic zirconia is I color. ln price increases by 0.14 relative to the base. And we can take the best one, dk6, if a cubic zirconia is D color, the best color. ln price increases by 0.5, where J is the base. Dummy variable DC, which is clarity. Base is I3 clarity. So DC2, if a cubic zirconia is I1, ln price decreases by 1.07 relative to the base. Same logic applies for all of them. And for DC8, the best one, if a cubic zirconia is VVS1, ln price decreases by 0.091. It's the best, so it has the least decrease effect on the Y variable compared to DC2, which is the second worst after I3. And I2, which was removed in the model selection, of course. For model validation, we used goodness of fit test, which I mentioned earlier, where the model was deemed good, F value was high, model was statistically significant. We can compare the root mean square error between the final model in the training set and the test root mean square error. These were similar, 0.13, 0.28, 128, which means that the model performs almost equally as well for the training and test set, which is a good model validation for the model. MAE is minimized. Is this a error term? It's supposed to be minimized. We can't compare this, but it's low enough to be deemed good in this case. Cross-validated R squared, final model had 98.34%. R2 test is 98.4%. The thumb rule is to be below 0.3, and the cross-validated R2 for our model is negative 0.0006. Therefore, it is good in this case. So for model validation, the model is deemed good. For the predictions were done on 6 observations, 1 observation for each dk dummy variable, all else equal. So for all of the predictions, a cubic zirconia with 0.5 carat, premium quality, and clarity of VVS1. We can then compare all of the different colors here from best to worst in this case. So a cubic zirconia with 0.5 carat is of premium quality, has a clarity of VVS1 and a color D. The price of that cubic zirconia would see a price increase of 210,049%, with a prediction interval between 208,000 and 212,000%. So the value might range between those prediction intervals. E-color, same logic applies, price increase of 198,000, prediction interval between 196 to 200,000. And once again, I want to emphasize that all else equal, so it has E-color with 0.5 carat, premium quality, and VVS1 clarity. And then we can go to the worst one, which is I color here. A price increase of 144,000% with a prediction interval between 142 and 145,000%. And that is once again for 0.5 carat, premium quality, and clarity of VVS1. So we can see here that the color does have an effect on the predicted price of a cubic zirconia. For future recommendation, the primary one is that we didn't use a polynomial model, as several variables were cubic, they were nonlinear. And by creating a polynomial model, we could capture the complexities and nonlinear patterns that existed in our data, including high-order terms such as quadratic or cubic terms, which would allow us to better represent these relationships and potentially improve the model's fit. Distributions of our variables, we used log transformations for variables like price and carat to force them to fit the model. It helped normalize the distributions and meet the assumptions, but we need to be cautious about the interpretability of the transform variables. Transformations can alter the scale and the meaning of the variables, which makes it challenging to directly interpret. And this is also the case where 210,000% increase, for example, it doesn't necessarily map to reality. Therefore, these interpretations have to be done carefully. Thank you for your attention, and I welcome any questions or discussions.